Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue and finish Chapter 8 on Polynomial Regression. All right, so when you've got polynomial regression with two predictors, you now have the ability in a three-dimensional space to create a two-dimensional surface that has curvature. And the general quadratic model, for example, we'll stick with quadratic models because they tend to give us adequate flexibility for most problems, and adding cubic and quartic and higher order terms makes things a bit too complicated to discuss. So here we're going to model a response variable y as an intercept. That's the value when the x values are equal to 0. A slope parameter in terms of x1 and x2. Then we've got quadratic terms in x1 and x2 that allows parabolic curvature in both of those directions. And then an interaction which allows basically a twisting of a plane. And I was reminded, reviewing this lecture, of a paper I wrote in 2007 for Stats Magazine. It used to be a publication of the American Statistical Association. It was a student magazine, and I published this as a student, about response surface methodology, which is a strategy for process improvement, and now a course that I've been teaching at UNM for several years. And in that paper, I discuss how to optimize the flight time of a paper helicopter. But I have this image on the right-hand side of different response surfaces, and I'm going to zoom in a little bit. I also have the equations for each of these response surfaces, and you can see in the equation we have that intercept term, we have a linear term in x1 and x2. The coefficients here is 1 and 2. We have a negative 2 for the coefficient for the x squared term, x1 squared term, and x2 squared term, coefficient of negative 3, and then an interaction. And these negative signs in front of the quadratic terms indicate that we're going to have downward curvature in those directions. So let me scroll up now to the images, and we'll just look at a few of these images. The one on the left, we actually don't care in our applications for modeling what the maximum is, but in response surface methodology, we want to find basically conditions of x1 and x2 that optimize the response or give us a maximum or possibly a minimum or maybe even a target value for those settings. And if we think here in terms of maximums, that's where the darkest red is. But the purpose here for us is to look at the shapes of these planes. So we've got x1 along this sort of horizontal axis. We have x2 along this axis going sort of front and back. And then the response variable y is on the vertical axis. And the shape here, you can see already, let me scroll back down to the equation for that first equation. We have coefficients for both linear terms, for both quadratic terms, and the interaction, multiplication between x1 and x2. This interaction is providing a twist of the hyperplane. So I scroll back up in this first image, you can see, how about for x1 at its low level of -4, how the slope, there is curvature here, right? It sort of goes up, but the slope starts to decrease as it heads toward the back as x2 increases. But when x1 is at the high level at +4, you can see it starts high and then curves downward and becomes more steep downward. And that's the component of the twisting that it's sort of hard to describe strictly in words, but you can sort of imagine having your hands, maybe a left hand holding the plane over here on the left and a right hand holding the plane here on the right, and pushing your right thumb downward and pulling your left thumb upward to twist this plane. Okay. If you imagine that, congratulations. That was impossible both to describe and to imagine. But you can also see curvature, right? There's this downward curvature in any direction that you see. Okay, and those are the result, if I page down just a little bit, of these negative signs in front of the quadratic terms. A few other things, I guess, there's a positive sign in front of the linear term, okay, both for x1 and x2, and we can see the result of that as well. You know what? That's actually going to be pretty hard to see, so I'm going to skip that. Okay. So a few shapes that you can get from this, and these are fairly limited selection of shapes because in the paper I was describing certain qualities. There's something called a stationary ridge where there's sort of a maximum that is a constant value, and so you can maybe you can see the twisting a little bit more in this one in part B on the one on the right than we could on the left. If I scroll down a bit, maybe the one that's most interesting is this one on the right. Oops, I don't know how to make that stop. This is called a saddle point or a minimax. In one direction, say from this blue corner across the center to this other blue corner, it goes up and then back down. And so there's a maximum in that direction at this orange section. However, if you start at the red corner and go down to the orange section, then back up to the red, in that direction there's a minimum. And so that's why that's called a saddle, as though you're sitting on a horse, on the saddle of a horse. Going from your leg to leg, you are sitting at the maximum in the direction sideways across the horse. But going front and back along the horse from, I don't know, equestrian terms, but if you're holding the saddle knob with your hand in front of you and it goes from in front of you to behind you, where you're sitting is a minimum. There's upward curvature in that direction. So you can sort of imagine that your legs are hanging down to these blue stirrups and you're holding on to a red part here facing along the horse. The horse is sort of along in the red direction. Okay, all that is to basically give you some idea of what these surfaces look like. Sometimes in this example that I'm going to show you with the Mooney viscosity, I have a simplified way of visualizing this in as pairs of two-dimensional plots, but I did want to show you some three-dimensional plots as well. All right, Mooney viscosity. Mooney viscosity is a measure of thickness of a liquid, right? So when you've got high viscosity, you have something sort of like cold honey, something that flows very, very slowly. And if you have low viscosity, you have something like water or alcohol that flows very quickly. And so this is a type of, this is a viscosity for a type of oil for, I guess, okay, that is measured at 100 degrees Celsius. Okay, so that's at the boiling point of water, as a function of the filler level. So there's some sort of filler that's going into this chemical compound, and an oil, naphthenic oil, and we're looking at an experiment that involves filled and plasticized elastomer compounds. Fantastic. All right, so if we just take a quick look at the data, we got 3 columns, and this is clearly an experiment because of how neatly the data values are, right? Oil is 0, 10, 20, and 40, and filler is in multiples of 12 from 0 up to 60, and then the Mooney viscosity is here on the right-hand column. And we see actually one missing value. They conducted the experiment, but maybe weren't able to obtain a measurement. All right, so I'll close that out. Back to the notes. And let's first plot the data, and I want to spend a moment discussing how I plotted these values. So I've got two plots. The one on the left has oil as the horizontal axis, and then the filler values, 0, 12, 24, and so on, are labeled points. And for example, you can see that the 60s are all at the top and the zeros are all at the bottom, and you can see that the missing value is here, the 0 value for filler and the value 40 for oil. On the right hand side, same thing. We've got the filler along the horizontal axis, and the labels are the oil values, 0 to 40. And right away you can see some curvature here. Okay, it's to me this is fairly parabolic, and maybe a main feature here is that there's low spread when the Mooney viscosity is close to 0, but then the spread increases as the Mooney viscosity increases. So that relationship between the mean and the spread is something that the log transformation is a good transformation for. It's what's called a variance stabilizing transformation. It's one that allows the mean and the variance to be independent from each other. And this is one of those nice examples where that works. Let's look at the code for this. You can see how tidy the code is. There's only basically 3 or 4 lines that's doing the plotting. The main feature here is on the left-hand plot I have oil along the horizontal axis, so X is oil, Y is Mooney, and a new argument here is label equals filler, and the labels are plotted with geom text. So notice I don't have any geom points here. There's no points, there's just the text, and the text that's being plotted are these labels. Beautiful. And then the only other parts are the scale, and the only reason I've added scale here is because I want 0 in the plot, even though the Mooney viscosity doesn't go all the way down to 0. I want 0 in there, and then I go, basically the limits are from 0 up to whatever the maximum viscosity is, and I'm going to ignore or remove missing values, NAs, before I compute the maximum. And then I've got the title there. All right, so I'll zoom out just a little bit, and you can see the warning here because the one row was removed that had the missing value when geom text was tried to plot the 0 value down here or the 40 value right there. All right, so we've got something that looks like parabolas might be able to fit it. Let's take a look at what happens. So we'll fit a linear model with Mooney viscosity as the response variable, and then I've got oil, filler, and then I'm using the I function to interpret the code inside to create new variables on the fly to fit this. So I've got oil squared, filler squared, and oil times filler is the interaction. And I'm putting that in this linear model object, and when I look at the summary, our model coefficients indicate that the interaction as well as the 2 quadratic terms are significant. So we're capturing much of the structure we saw in the plots above. And this is the thing that you only see in sort of designed experiments with physical systems that you can model pretty well. 99% variability explained with this model. Let's make sure that the diagnostics look fine. Actually, before I do that, I want to describe, I've got a comment here about this poly function, which would allow us to simplify some modeling note syntax. Let me page up for a second, if we wanted to. So say we had a lot of variables, oil, filler, and 5 others, and we wanted all the quadratic terms and their two-way interactions. That would be a lot of typing. So if I page back down, the poly function will evaluate variables and give joint polynomial values when you've got main predictors. So maybe just try copying and pasting and see what this looks like. Okay, I've got, one interesting thing, and when I compile this, my dollar signs become pound sterling signs in these comments. I don't know why, but this is Mooney oil, comma Mooney $ filler. Degree equals 2. And so if you take a look at what the poly function is doing here, you'll see columns for the main effects and the quadratic terms and the two-way interaction. And then you can fiddle in your model just like this. Mooney tilde poly, I want of oil and filler, and I want it to be a second degree polynomial. So those quadratic terms. So that will actually give you the same model as what we did above. Okay, so let's take back to looking at the residual plots. So we potentially have maybe two influential observations that we want to take a look at. Observation 20 is influential largely because it has high leverage, and observation 6, same thing. Here's observation 6 there, and observation 20 down here. Now I've got these numbers which are being plotted, and I've chosen, if I scroll up just a little bit, I've used my plotting character PCH as character and the values or the labels for the filler and oil. The challenge here a little bit is that when we use as character as the plotting character, when I have a 2-digit number, it only plots the first digit. But in this case, if I page up for a moment, that is actually going to be sufficient. Actually, where a better place to go is back to the data, because the first value is unique for each level. So I've got oil is 0, 10, 20, and 40. That's going to appear as 0, 1, 2, and 4. So same thing for filler. These numbers are going to appear as 0, 1, 2, 3, 4, and 6. Okay, so if I page back down to here, right here I'm using the oil levels that have 0, 10, 20, and 40. And maybe there's a little bit of curvature here. I don't know. It's hard to say. These two definitely seem unusual. These highest fitted values seem unusual here. And I think the reason we're getting that is because of the dependency between the variance and the mean. These other plots don't look too bad. We're looking for equal variance here, and with 6 observations each, we're not maybe seeing a lot. Same thing, 4 observations each. It's hard to say whether those are equal variance or not. Residuals look pretty normal otherwise. But because we saw that dependency of mean and variance, let's take a look at the log scale to see whether we can improve our modeling. Because, actually in the normality, as part of the normality assumption, we assume that the variances are equal, but I don't think that's really it. In fact, let me scroll up a little bit. Maybe we can see that in these plots. A little bit hard to see. I was going to see if I could see it in the residuals versus fitted, that we'd have more variance where we have larger fitted values and smaller variances elsewhere. And maybe a little bit hard to see here. Okay. Well, let's take a look at the log scale. Here is what the data look like. And this is fantastic, right? So I'm going to start on the right. The filler values, look at these zeros. Basically all line up. The 10s all line up. The 20s all line up. And the 40s all line up. Okay? Over here on the left, however, oil, these first 3 seem to line up for each group. But then, if we follow the 60s down, 60, 60, 60, 60, we'd sort of expect the 60 to be about there, but it's higher. And that's the same for all the sets. Even 12 actually looks like it's starting to have a little bit of curvature even on the third one, and then curves a little bit more. So there's some amount of curvature here to capture this when the oil is at 40. So I'm expecting then on the right basically straight lines, and on the left maybe a bit of a curvature. So with respect to filler, I don't expect a quadratic, but maybe with oil. So let's take a look. So here I'm fitting the full model again, but I've created this new variable log Mooney above that I'm using as the response variable. And we see right away that in the coefficient table that the quadratic terms for filler and the interaction between oil and filler are not significant. Now, this is a point where we get to do model selection consistent with the hierarchy. And in fact, it's the case that I could drop either of these variables first, because we've got the main effects in the model. So so oil by filler interaction depends on the two main effects. So that's fine. And filler squared depends on the filler main effect. So all the dependencies are still in the model. I could drop either one. Probably makes sense to drop the one with the largest p-value. So I think I just put in a comment here. Well, okay, we'll take a look at the residuals first. These in fact look even better. There's maybe one influential point, observation 6, which is partly because it has high leverage, but boy, in terms of the equivariance assumption, these look better. Normality looks fine. So possibly one influential observation. And so I'm going to omit the interaction term first, and if I refit the model, then the quadratic for filler is still not needed, so I will also remove that one. So I'm doing it one at a time, and once those two are removed, I'll fit this model with has oil squared, and filler, and now everything is significant. And look again at this R squared, 99.47%. And if we take a look at the residuals, these pretty much look great. This little bit of a curvature that the red line is suggesting, I don't think there's a lot of evidence. There's 2 points down here which are sort of making that line come down a bit, and I just don't think we have the sample size to say that there's missing structure in the data that we haven't seen or haven't captured with our model. So if we plug in the model coefficients, we've got basically 3.2 on the log scale. The log Mooney viscosity, and the hat is the estimate, means that we're predicting this. So we're predicting the log Mooney viscosity, intercept, coefficient for oil. You can see the coefficient for the quadratic is very, very small. That's not unusual. That will often be the case. So maybe a small coefficient, but it can have an important effect on the model fit. And then linear term for filler. And that's all she wrote. And by she, I mean me. So a couple maybe takeaways here, if I page back up. We started with data that had curvature and had this problem of that the mean and the variance were related to each other. And by taking the log of the response variable, we found, and another thing is when we, that fitted model had all the quadratic terms and the interaction important as significant, and that makes for a more complicated model to interpret. By taking the log, we found that not only did we fix the mean and variance relationship, but we ended up with a simpler model in that it was linear with respect to filler. The log Mooney viscosity was linear with respect to filler, and had this slight quadratic curvature with respect to oil. So we improved our model in several ways. One, by fixing the relationship between mean and variance, and second, by making it simpler. So I think those are two good lessons from this data set.